In Chapter 3, Part 3, Formula Weights, Avogadro's number, and the mole, we're going to learn about how we can think about chemical compounds in terms of things that we can measure. So when we think about a chemical product or a chemical component, we want to think about that in terms of grams, which is something we can actually measure. So if you wanted to create something, it doesn't make a lot of sense. We want to use NaCl or sodium chloride. I can't really weigh out, I don't have a scale that will allow me to weigh out 90 sodium chloride. Okay, there's no way for me to do that. So what we're going to do is we're going to start to think about the formula weight, like how much sodium chloride is sodium chloride. And if I have a fistful of that, what does that look like? How much does that weigh? What does the weight in grams mean? So to calculate the formula weight, which is the sum of the atomic weights for all of the atoms in the chemical formula. So the formula weight, So the formula weight is just how many AMU for a compound. So we're not quite to grams, but let's think about the formula weight. So the formula weight for sulfuric acid. Now, sulfuric acid is H2SO4. We're just going to add up the atomic weights. So we have 2 hydrogens, a single sulfur, and 4 oxygens. And so now we're going to look at our periodic table, which hopefully you have a copy of. And so we're going to be able to say, like, how much does hydrogen weigh? So every periodic table has a different number of decimal places. Some have 2, some have 5. What are we going to do? How do we make it the same? We are going to use 2 decimal places. So for hydrogen, it will be 2 times 1.01 AMU. For sulfur, it is 31 times 32.07 AMU. The oxygen is 4 times 16 AMU. And when we total those up, we get 98.09 atomic mass units. So the formula weight for sulfuric acid is 98.09 atomic mass units. And so I just want to write this out. For weights on the periodic table, round to 2 decimal places. So we're going to do this every time we see it. All of these solutions will be using these numbers. So this is what I will use. This is what I expect you to use. So when we think about formula weights for any component, for an element, the formula weight is the atomic weight. So anything we see on the periodic table reads directly off. So if we think about zinc on the periodic table, we can see that it is 65.38 atomic mass units. And so that's what it is. For an element, that's what we see. For a molecule, like sulfuric acid, the sum of the atomic weights for all of the elements present in the compound is the molecular weight. So you will hear me use formula weight, and molecular weight. Very shortly, we are going to switch to only molecular weights and leave our formula weights behind. Most of the time, those are interchangeable. So let's practice. So let's calculate the formula weight for sucrose. So in this case, sucrose is not something that we've learned in this class. We know it's sugar, or maybe we do, maybe we don't. But in this case, sucrose gives us the chemical formula. So we know it is 12 carbons, 22 hydrogens, and 11 oxygens, to where we're going to have 12 multiplied by the atomic mass, which is 12.01 AMU. And then there are 22 times 1.01 atomic mass units for hydrogen, and 11 times 16.00 atomic mass units. Oops. So when we add this all up in our calculator, what we will get is 342 times 3.34 atomic mass units. So we're just going to look at the periodic table, determine the atomic weights for any element, and go from there. Now, what about calcium nitrate? So calcium nitrate, this is something we need to learn how to name. So we know that calcium is Ca. Based on the periodic table, it's 2+. Nitrate is a polyatomic that's NO3-. The chemical formula for calcium nitrate will be CaNO3 2. So now we just need to do the same thing as before and total up the atomic weights for all of the elements in this component. So we have 1 calcium, 2 nitrogens, and 6 oxygens. So in that case, we can get that from the fact that the parentheses means there's double of everything inside. So calcium is going to be 1 times 40.08 atomic mass units. Nitrogen will be 2 times 14.01 AMU. And oxygen is 6 times 16.00 AMU. When we total those up, we will get 164.10 atomic mass units. So in this case, the formula weight for anything is just a total of what we see in the periodic table. So atomic mass units still aren't really something that we can measure on the scale. The scale in my house reads in pounds or kilograms. The scales in the labs read in grams or subunits of grams, milligrams or like decigrams. None of those really are atomic mass units. So what we need is the ability to convert between those. So in the 1840s, Amadeo Avogadro, not avocado, Avogadro, calculated that in 12.00 grams of carbon-12, there were exactly 6.022 times 10 to the 23rd carbon-12 atoms. So he did this through some calculations we'll see in chapter 10. And so what he's saying is, okay, in here, what we see, there are 12 grams of carbon-12, and that has exactly 6.022 times 10 to the 23rd atoms. So he describes this as the mole. So we often hear something that says 1 mole equals 6.022 times 10 to the 23rd. In this case, we're talking about atoms, but we really can think about terms of a mole as anything. A mole is just 6.022 times 10 to the 23rd of anything. Atoms, moles, elephants, potatoes, feathers, etc. So in this case, what we've realized is that the weight of all other elements is scaled to the weight of 12.00 grams. So if you remember back to chapter 2, they calculated the atomic mass units also based on carbon-12. So what we can figure out here is that atomic mass units equals, so the atomic mass units equals the number of grams in 1 mole for any given compound. So the atomic weight of an element in atomic mass units is numerically equivalent to the mass in grams of 1 mole. So if we look at these 3 things, we can see that chlorine is 35.45 atomic mass units. So that is 35.45 grams per mole. Same with gold. Now what about water? So water, the molar mass, is 18.02. And so we got that by 2 times 1.01 grams per mole times 1 times 16.00 grams per mole. And that totals up to 18.02 grams per mole. So we're going to just ignore this. because it's in the previous line. So the next thing we're going to think about is indium sulfate. So again, these are things that we want to start to kind of think about. So indium is In, and it has a 3 minus. And so sulfate is SO4 2 minus. And so in this case, we have indium 2 SO4 3. And so from here, we can start to think about what is the molar mass of that. So from here, we can do the same thing we've been thinking about. We have 2 indium atoms. We have 3 sulfurs, and there are, in fact, 12 oxygens. So don't forget that 3 times 4 needs to be propagated both over the oxygens and over the sulfur. So indium weighs 2 times 114.82 grams. Sulfur is 3 times 32.07. And it's 12 times 16.00. When we total all of these up in our calculator, we'll get 517.85 grams per mole. So what we can see is that the atomic weight for any component, or the molar mass, so the molar mass just means the weight in moles, we can calculate that using grams per mole. So the way we like to use Avogadro's number is to convert between different components. So you can convert between atoms and moles, and atoms, moles, and grams. So we want to calculate the number of hydrogen atoms in 0.350 moles of C6H12O6. So what are we going to do? Now, we're going to use dimensional analysis. Dimensional analysis is going to allow us to convert by canceling units. So we're going to take our 0.350 moles of C6H12O6, and we're going to say that in 1 mole, there are 6.022 times 10 to the 23rd C6H12O6. So there are 6.022 times 10 to the 23rd. This is glucose molecules. And so then we're going to say in 1 C6H12O6, there are 12 hydrogen atoms. So then we're going to be able to cancel out our units. So here the moles are going to cancel, the C6H12s. So our answer will be in hydrogen atoms, which is the goal. So then we can plug all this into our calculator and get 2.53 times 10 to the 24th hydrogen atoms. Now, a side note about significant figures. In this problem, there's only one thing that can give us a significant figure, and it's this value here. And so this actually has 3 significant figures, right? Zeros in front do not. So your final answer needs to be trimmed back to having the right number of significant figures. So our next example is how many oxygen atoms are in 0.25 moles of calcium nitrate. So we're going to take a very similar thing of 0.25 moles of CaNO3, 2, and then 1 mole of CaNO3, 2, there are 6.022 times 10 to the 23rd CaNO3, 2 molecules. So next, we're going to say that in 1 CaNO3 times 2, there are 6 O atoms. Now, it's important to write the word atoms next to this so that you don't actually think it says 60. It gets a little confusing with oxygen because it looks a little bit like a number. When we plug this into our calculator, we get that 9.0 times 10 to the 23rd O atoms. So we can just plug those into our calculator and then go from there. So we can now convert from moles to atoms very easily. The other thing we can do is to start to think about how many moles are in 5 grams of sodium chloride or any other component. And so in order to do this, we're going to do more unit conversions. So if we know the molar mass of sodium chloride, we can use that to convert from grams to moles. And we're going to do that a lot in Gen Chem 1. So the molar mass is the mass of sodium plus the mass of chloride. And so sodium is 22.99 plus 35.43, which gives us a total of 58.44 grams per mole. So if we know the number of grams per mole, we can use this to calculate the number of moles in a given value of grams. So we have 5.00 grams of NaCl. Now we're going to use our molar mass, which is 58.44 grams in 1 mole of NaCl. Whoops, forgot the L there. So when we plug this into our calculator, we got 0.85 0.0856 moles of NaCl. Now, you might be thinking, what are the sig figs in this? So what about the significant figures that come from the molar mass? So it turns out that the molar mass significant figures over here, or in any of the other cases where we calculate that, those significant figures do not affect. So the molar mass does not change the significant figures for any problem. So it might feel like it could or should, but it doesn't. So these, we're going to treat them a lot like unit conversions. So now, instead of going from grams to moles, can we convert from grams or from moles to grams? And we can. So first we need the mass of calcium nitrate, or the molecular weight. So for calcium nitrate, the molecular weight is equal to Ca plus 2N plus 6 oxygen, which is 40.08, 2 times 14.01, and 6 times 16.00. And so that gives us 164.1. That's hard to read. 164.10 grams per mole. So this tells us that if you were to weigh out 164.10 grams of calcium nitrate, you would have 1 mole of calcium nitrate. And so we're looking for the amount of grams in this case, and so it is 0.433 moles of calcium nitrate. And in 1 mole of calcium nitrate, there are 164.10 grams of calcium nitrate. And so in this case, our final answer is going to be 71.06 grams of calcium nitrate. So you might look at these two different equations and say, well, on one of them we put the mass on the bottom and one we put it on the top. So unit conversions, which is a lot of what this is, the thing we want to remember is to think about, if we're looking for grams here, we need grams to be on the bottom down here. So in this other one, we have moles at the top. So if we'd put grams on the bottom, we would have ended up with moles squared per gram, which is not the unit we were looking for. So we always want to make sure that we're keeping track of our units so that we can actually complete the calculations.